So here is your video for 5.5. 5.5 really, even though it has some crazy looking formulas, is not as bad as it actually looks. The first part is really just a refresher about change of base and solving exponential equations using logarithms, and I'll do one of those so that way you can kind of remember. As soon as you see it, you'll remember. And then, of course, it's about taking the derivative. We have this little rule, which may or may not really be all that exciting. Because we have all of these other little rules of converting your log with a base that is not a common log over into a natural log. And then we have two derivative rules where you got a to the x, and the derivative of that's going to be the ln of a times the quantity a to the x. But of course, we're most likely using a to the u, so it would be ln of a to the u, and then of course your du. That would be Abby barking. And then you got log base a of x, which is going to be 1 over x times the ln of a. And in the textbook, they write it ln of a in parentheses and then the x. I kind of like it this way. I don't care how you write it. Either way is fine. Of course, it could be most likely dealing with u, so 1 over u ln of a times du. Yes, and again, they write that one in the book backwards as well. And then there's only one in this section for an integral, so finding the a to antiderivative, and I got the integral of a to the x dx, 1 over ln of a to the x plus c, and of course, we're probably going to have u's in there instead of those x's. So I have a couple of different examples. This one is the one that is kind of the refresher from pre-calc, where you want to solve this equation, go 3 decimal places. Let's see if I can get my calculator working. It didn't want to cooperate before. Calculator. That's not it. Oh, calc. Let's see if you want to work. Okay. So, if I have this and I want to solve this, first of all, I'm going to get rid of this 6 and divide both sides by a 6 so that I get a x to the negative 9, 89 divided by 6, which is probably not going to be nice, I don't think. No, so we'll just go ahead and leave it like that. And now what we're going to do, there's a couple of different methods that you could do. I would probably just take the ln of both sides. So what happens is that this side you're going to get some kind of crazy looking number, and we'll just leave it as is for right now. And then over here what happens is that I can now pull down that x minus 9 out front, and then I have this ln of a over here. So that I get x minus 9. Remember, ln of 8 is just another ugly number, so they get the ln of 89 over 6 divided by the ln of 8, whatever the heck that is. The calculator knows. Let's see, the ln of 89 over 6 is that, and we will divide it by the ln of 8, and we get that. So basically we have x minus 9 equal to this guy right here. So then all I need to do is add 9 to both sides, plus 9. And they want 3 decimal places, so how about 10.297? 10.297. And that should be my winner. They look kind of crazy looking, and the numbers will always be really ugly, but they're pretty easy to do thanks to our handy dandy calculator. So now if we want to find the derivative, we're going to need to use our functions. I have an f of x or a y equal to basically a to the u. So in this case, u is a negative 6x, which means du is going to be negative 6. And so my formula is the derivative of a to the u, and a is a regular whole number, a positive real number that's not equal to 1. It's not going to be like some kind of binomial or something in there. And that is the ln of a times a to the u, and then my du. So this lovely derivative is going to be the ln of a, which is a 5, times a to the u So 5 to the negative 6x, and then times my du, so times a negative 6x. Kind of like e, they don't like to go away, and they come back, and sometimes they bring extra stuff with them. So you're still going to want to use your u substitution for your exponents, things underneath radicals, things inside trig equations like that. Another one, and this one's going to be a quotient rule. So remember, quotient rule is g f prime minus f g prime over g squared. And so let's make him f and this guy g, and we will find the antiderivative. So let's see, f, well, g, let's write the g squared down here first. And then I have 8 to the 6t, and I'm going to find the derivative of basically a to the u, right? So that's going to be the ln of a times the a to the u times du. So chain rule, basically, right? Now, times something, g, minus a whole bunch of stuff. G prime is a 1. Well, that's nice. And then just f. So how about 8 to the 6t? And what we can do, it's a little sneaky looking. If you want to clean it up, is we can actually factor out this guy. Oh, that's not what I wanted to do. That's what I wanted to do. So we can factor out the 8 to the 6t and have 6t ln of 8 in here, right? Because I pull him out. Those two guys can be multiplied together. Stick him out front. Minus 1 all over a very slanty t squared. So I think the worst part in this section is remembering that you're taking derivatives and not antiderivatives. Another rule that we had from the front part was that log base a to the of x, or in this case of u, and that derivative was when you have something that looks like that, is 1 over the u times the ln of a, and then you have your du dx out here, right? So all of this is going to be u. So if u is x squared minus 7x, then du must be 2x minus 7, with my a being a 6. So I have 1 over u, which is x squared minus 7x, ln of a, which is 6, times my lovely derivative, which is a 2x minus 7. And then you can put him up top, and you can see it would be awfully nice taking the antiderivative, right? Because the antiderivative you would say, oh, let this thing be u, and then this is du, and you got the ln of 6 down here, and so that you would be able to just go right back using those other formulas. Here's our one and only integral rule that I saw in 5.5, and that is if you have, let me remember, I have a to the x dx, in this case we'll have a to the u. I have 1 over the ln of a, that times nobody, times out here a to the x. Well, I don't have quite what I want, right? Because I have not just an x up there, I have a u. So if I let u equal 1/2 of x, then du is nicely a 1/2. So I can go ahead and put a 2 out here and shove a 1/2 in right there, so that I now can pull him out and say, oh, well, this guy is now 2 times -2 from the -2 to the +2 of the 36u du. So that means my antiderivative way out. Actually, I'm going to move that. Because I got this 2 floating around on the outside, and then I'm going to need to do all of that other integral stuff and then multiply by a 2. Is going to be 1 over the ln of a is 36 times a to the u. Of course, u is 1/2 of x. Let's write him like that. And we are going, ooh, a little crooked, huh? Negative 2 to the 2. So we will plug this lovely stuff in here and say 2 on the outside. And I have, if I plug in a negative 2, I get 36 to the negative 1 over the ln of 6. Oh, we want the positive first. Ooh. $36. And then 36, if I put in the positive first, I get a positive 1. So 36. Minus 36, here's my negative 1. The ln of 36. Down here. Calculator. Let's see. 36 over the ln of a 36. Kind of looks odd, doesn't it? Enter. That minus 1 over, remember that 36 is just going to drop down and be a coefficient. Actually, we may want to go ahead and put parentheses for that denominator. Close the log, close the denominator, close the fraction. And so we get that times 2. So how about a, come back, 20 point, wherever they wanted us to round to, I'll write 20.07. And actually, I just checked. They wanted it in this form. And so I had to type that whole thing in just to make sure that I wasn't lying to you. And you can see that you're good there. And that's the bulk of that section. I think it looks a lot worse than it really is. But it's not, certainly not the worst section that we've done. And that's 5-5.